Welcome to the video lecture for March 27th. This lecture focuses on the exponential model of growth with the following goals. I will show you how to identify when feedbacks in a system can be modeled by an exponential model, and I will show you how to use a formula for the exponential model and apply it to a bacteria population. As part of our work on the exponential model, I've posted a warm-up in the Sakai forums on folding paper. You can take a look at this warm-up now or after you've finished watching the video lecture. Let's remind ourselves where we left off in our last class. We're interested in understanding stock flow systems that are not in equilibrium. To do this, we analyzed feedback loops, instances where the level of a certain stock directly or indirectly affects the flows to that same stock. I presented two examples: the feedback loop between the stock of water in a bathtub and the outflow through the drain, and the feedback loop between a bank account balance and the interest earned. You also worked through several examples yourself. In some circumstances, we can use the feedback loop to describe the stock levels using an exponential model. An exponential model applies to a stock flow system if the stock level directly affects its net flow, and if the net flow is proportional to the stock level. Let's look at an example from the last activity, bacteria growth. In this model, the bacteria population is the stock. New bacteria are created by cell division. As bacteria cells grow, the bacteria population increases, so the cell division represents an inflow to the stock. Since each cell divides into two, the new cells are proportional to the number of old cells. If we use B to represent the number of bacteria, then we can say that the inflow is equal to 2 times the B, the bacteria population. For certain types of bacteria, this cell division takes place approximately every 20 minutes. So the units here are cells per 20 minutes. Note that the flow rate is proportional to the stock, so this is an exponential model. One of the reasons why we consider exponential models is because we can create a mathematical formula to describe the stock levels over time. To do this, we need to determine the time step for the model, the rate constant, and the initial stock level. Then the stock level is given by either of the two formulas shown, where we can focus on the number of time steps that have passed, the first formula, or the overall time passed, the second formula. In order to understand these formulas better, let's look at the bacteria example. Bacteria double every 20 minutes. This means that every 20 minutes, there are 100% more bacteria than there were previously. So in this case, the time step, T, is equal to 20 minutes. And the rate constant, R, is equal to 100%, which we normally write in decimal form. So in this case, it would be 1. Suppose we start with a bacteria colony with a single bacteria. Then S0 is equal to 1. Our formula then becomes S is equal to 1 times 1 plus 1 to the n, or 2 to the n. If we wanted to predict how many bacteria there will be after 1 hour, this corresponds to 3 time steps. We'd get S is equal to 2 to the third, or 8 bacteria cells. There will be 8 bacteria after 1 hour.